minutes. All right. So, finally, calculus. You guys remember calculus? How do you start calculus? Do you remember what we did while you were waiting? You knew in your heart that the course was about differentiation. What were you doing for like a month in your course? Limits. And you guys are like, we love limits. We missed limits. We so want to go back to limits, right? So, now is the time in the course when I tell you, I don't really test you on limits in here. We should define the derivative in our current context in terms of limits, and I will. But I will make a definition, and then we will quickly point out that we can trade that definition for derivatives of component functions, and we're just going to stay there and not do proofs in terms of limits in here, because it really is not the right way to think. And so I want us to spend the lion's share of our time in the right way of thinking about derivatives for calculus 3. Now, before I talk about differentiation, I probably should talk about what are we differentiating, right? So we're going to talk about the derivatives of paths, or if you like, vector valued functions of a real variable. All right, so let me just get that ugly limit definition out of the way. Just get it out of the way here. So here's our definition. If R is a mapping from I, which is a subset of the real numbers, to Rn, then R prime of T naught is equal to the limit as h goes to 0 of R of T naught plus h minus R of T naught, all divided by h. This is the definition of the derivative of the path. So here, this kind of thing we call a path. Or some people call it a space curve. Doesn't that sounds pretty cool, right? Space curve. We also talk about force fields in here, right? Force fields used to be cool. Then Disney got Star Wars. But anyway, I'm sorry, I digress. No, we'll not digress further. So, look, let me draw a picture of this in 3 dimensions. So what's going on here, if you want to picture it, we've got, some curve, whee, right? And so here is perhaps R of T naught, right? And then maybe over here is R of T naught plus h, right? And what is this thing in the numerator of the thing I'm limiting? What is that? I'm gonna draw my picture as if h is positive, okay? If that's all right. So I'm assuming that the curve goes this way, all right? And I'm assuming h is positive for my picture just for the sake of specificity. So isn't this vector exactly the one that connects the displacement vector from here to here, right? It's maybe I would call it delta r. Delta r is R of T naught plus h minus R of T naught. Do you guys see that? Because if I add the displacement vector to T naught, I get R of T naught plus h. So really, in another notation, what I'm calculating is just the limit as h goes to 0 of delta r over, well, let me call this delta t. Instead of h, let's say delta t, right? Then that makes it look more physicsy, right? Just letting h equal to delta t. So what is this? What are we calculating? We're calculating the limit of the average velocity vector, where average velocity vector is defined to be like the displacement vector divided by the change in time. We're letting the limit of the change in time going to 0. So this is a natural generalization of our definition of derivative in calculus 1, right? We're taking, it's the instantaneous rate of change of the vector function. Geometrically, what's it doing? If this thing exists, what should it be? The tangent, right? But is it a tangent? Is it a number? What is the tangent in 3 dimensions or n dimensions? It's got to be a vector, right? So the tangent line, the natural way to talk about that. Do you want to talk about it in terms of symmetric equations? I don't, right? So the natural description of tangent line is the parametric description. So if I'm able to, well, my picture is getting kind of a little bit busy, but there's a line in here, right? And that should have direction vector r prime of t naught, right? Supposing it exists, right? Does this limit have to exist? Certainly not, right? But if it does exist, then the path is said to be differentiable, and that's its derivative. The derivative is the direction vector to the tangent line to the space curve at the point if it exists. All right. So let me just tell you this. And so this is the place where I'm not going to prove things, I'm just going to tell you, okay? If r is equal to, let's say, x, y, z, right? All functions of t. You guys with me? Then the limit of the r vector is equal to the limit of the x function, the limit of the y function, comma, the limit of the z function. In other words, the limit of a vector valued function is the vector of the limits of the component functions, provided they exist. So what that means, guys, is that this is a theorem of advanced calculus, all right? So with that theorem, and listen, we're about like 2 minutes from limits being gone, so just hang with me here for a second. So r prime is the limit as h goes to 0 of that, right? Let me use the delta notation. Delta r, delta over 8. Fine. Oh, my bad. Do you guys want me to go with, so you guys' choice. You choose your own adventure. You want to use h or delta t? Delta t, all right. So limit as delta t goes to 0 of delta r over delta t, right? So advanced calculus essentially says that this is in fact the limit as delta t goes to 0 of delta x over delta t, limit as delta t goes to 0 of delta y over delta t, comma, limit as delta t goes to 0 of delta z over delta t. Oh, goodness gracious, right? But what are those? Well, those, right, with the understanding this is all being done at t naught, those are exactly just the derivatives of the x function, the y function, and the z function. So it's literally just, x prime of t naught, y prime of t naught, z prime of t naught. That's it. So to calculate the derivative of a space curve, we simply differentiate the component functions one at a time and string them together. It's just that. That's the derivative. And we could take that as our definition, and I do some semesters, but I then feel guilty about not at least having this discussion, because this discussion is important because it helps you understand why the derivative gives you the direction vector to the tangent line. Yep.
Wouldn't that not always produce a line because x prime, y prime, z prime?
But x prime, y prime, z prime are evaluated at the point of tangency. They have to be evaluated at t naught. So they're not functions of time. So well, let me talk about what you're talking about here. Example 1. Let's explore Sam's question further. So here's a good one. R of t is, let's start out with this one. T squared, t cubed, all right? I'll try to show you guys how to visualize this in a bit. Of course, you can use Mathematica if you're like good on that and you like to use that. You're welcome to do it. I haven't used Mathematica for about a decade, so it would take me a minute to like get back up to speed with it. I tend to use something else, drawing, but like I can get pretty much everything done with drawing in this class. Now, three-dimensional visualization, like the website I linked you guys to, that is, I'll show you, it's really, really cool. It's a nice way, but anyway, so let's calculate the derivative here. So dr dt, and so this is just basically the theorem that I'm not really proving, but I'm just telling you it's true. So if you like, we can take this as our definition, all right? Let's take our definition to be this, that this is, curses. Well, let me not write it down. Our definition of the derivative of a space curve is that it is the, fine. Definition. If r equals to x comma y comma z, then dr dt equals to dx dt, dy dt, dz dt. All right, or if you want me to be more annoying, if r is equal to a sum over I of xi x hat I, then dr dt equals to the sum over I of dxi dt xi hat. This is all just a fancy way of saying to differentiate a space curve, you simply differentiate the component functions. That's it. And if any one of those derivatives doesn't exist, we say that the space curve is not differentiable. All right? So what's this? We've got 1, 2t, 3t squared. Now, that is itself another space curve, isn't it? Right? I mean, you could think of it that way. So let me try to foolishly picture this thing. What's it look like? The original path, t squared, t cubed. This is called the twisted cubic. So it does something kind of sort of like this. I mean, it just maybe not even that. Let's see here. I'm not doing it justice. Well, here I'm assuming t is greater than or equal to 0, let's say. Tell you what, let me not try to draw a picture of it. Let me get my computer out and show you what it looks like in a second, all right? That's okay? I mean, that is roughly a picture of it, but I don't know if you get much out of that picture here. Oh, you know what we can do? Let me not be dummy. Let's just look at t equals to 0. That gives us what? R of 0 is 0, 0, 0, right? How about t equals to 1? Where does that get us to? 1, 1, 1, right? How about t equals to 2? 2, 4, 8, right? And let's see here. So this one has what? It has x equals to t, y equals to t squared, right? Which is equal to x squared. So if you were to look at the projection of this curve into the xy plane, you'd see that it follows the parabola y equals x squared. So if I was to foolishly attempt to graph it, it would be like over if you were to imagine this, it would be like, oh, so if y equals x squared up to the limits of my artistry is something like this here, right? Like in the xy plane, if you can imagine it. And this thing is, it's going up over that, right? But it's going up over that at a cubic rate. So it's like growing like mad. So it's something like, I don't know, that's pretty much all I can do here. It's just a curve that starts at the origin and then it just goes up. And the meaning of this, right? The meaning of this is that if you fix any t, that's the direction in which the curve is going. See, the bigger t is, the more upward pointing it is. Like at t equals to 10, its rate of change is 1, 20, 300. Right? So it's the curve is getting more and more vertical and less sort of horizontally changing as you get further and further. It becomes more and more just like straight up. All right? But I'm talking about different times, right? If we fix a particular time, we can find the parameterization of the tangent line. So let's do that. Find parameterization of tangent line to curve at t equals to 1, right? So at t equals to 1, what do we got? R of 1 is what? 1, 1, 1, right? What's R prime of 1? 1, 2, 3, right. And so, thus, if we do, let's say, L of t equals to R naught plus t times R prime, R prime of t naught, that would give me a parameterization of the tangent line at t naught. All right. Now, what if I want, yeah?
That's supposed to be the brackets on R1 and R2.
It doesn't matter. But yeah, I probably should definitely write brackets on, I definitely mean brackets for this one for sure. Fair enough. Like your comment's not wrong. Because I'm thinking of that as a vector. I try to think of vectors in terms of the bracket notation. So like I add without brackets to brackets. This is I'm using the point vector correspondence when I do that. That would be like wholly inappropriate on a curved space. Like I couldn't do that if I was working with vectors on a curved space where you can't just add them at different points. But in flat space, we're able to do this. And most of the equations of physics and engineering are based on this assumption. So I try to build it into the course. As being more careful and rigorous in that regard would like not be healthy for you in terms of interpreting it in other courses. Even though we could do that. I've started writing notes doing that, and then after about 20 pages I was like, oh, this is not good what I'm doing. So I stopped. But so for me, it's just a point of emphasis. I'm thinking of this as a vector, and I am thinking of that as a vector. It's the direction vector to the curve, to your right. Now, so here, we've got 1, 1, 1 plus t times 1, 2, 3. There you go. That's the parameterization of the tangent line. Now, the weird thing is that makes t equals to 0 the point of tangency for the tangent line, right? Whereas t equals to 1 is where the curve is at that time. So if you want to make the parameter for the tangent line have the same sort of temporal meaning as the parameterization for the tangent line itself, if you want to think about the parameters being time, honest to goodness time, and you want the tangent line to collide with your curve, then instead of using this, if you want the colliding tangent line, pretty simple. You just do L of t, I'll say L collide of t equals to, for our example, 1, 1, 1 plus parentheses t minus 1, 1, 2, 3. And then, as you can see, L collide of 1 is equal to R of 1 is equal to the point of tangency 1, 1, 1. But up to the limits of my artistry, the tangent line we're looking at here is, you know, something like this. So here's your L. Like that might be L of t, for example. I would call it, the colliding tangent line is made such that if you were to track motion along the green line and the blue line at once, if they were colliding, it would be such that as t progresses, they both come to that same point, and then they go off. So now you might say, well, which is right? Is it right to make the colliding line, the tangent line, colliding or not colliding? Like, what's the answer to that? I mean, that question betrays a deeper question, which is, what is the right parameterization for a curve? Do you guys have an answer to that? Like, there's not a right answer to that. There's infinitely many different ways to parameterize a curve. They're all different descriptions of the same geometric object, right? That's just a ambiguity we have to deal with in the parametric viewpoint. Okay, so are we good on this? If I ask you to find the tangent line to a parameterized curve, what's the procedure? You differentiate it, right? You plug in the point where you're interested in this case t equals 1. That gives you the direction vector of the tangent line. And then you go back to what we did before. The equation for a tangent line, or for a line, is the base point plus t times the direction vector. Or if you want to be fussy and you want it to collide, you can adjust the t to be t minus 1 to make things. Or if my tangent line was at t equals to 10, I'd put t minus 10 there, right? So generally speaking, t minus t naught makes it collide at t naught. All right, let me erase this jibber jabber over here. So let's set aside the geometry for a second and let's just talk about the calculus, all right? The calculus is so nice. It's so nice. So let's let A and B be functions from the reals to R3 for the sake of specificity. And let's let F just be, a function from the reals to the reals. Right? So in particular, here we go. d dt of A plus B. What if you take the sum of two vector valued functions of time? Guess what? The derivative of a sum is the sum of the derivatives. So that's pretty nice. Really not that surprising. How about if you've got a scalar function of time multiplying A, like dfa? How's that go? So notice that f is a function of time. What do you think the rule is going to be?
You can take it out.
F is a function of time. Can we take, so if f was constant, I'd be totally with you. It'd just be f times df dA. Absolutely, you're right. Yeah. Yeah? So yeah, df, so you said f prime a plus f a prime. Yeah, I just, I like this notation because it emphasizes more it's more in your face where the derivative is, right? How do you prove this? Let's prove this. How do we prove that? So I'll give you a two-dimensional proof, right? 2D proof. d dt of fa. What's fa? Well, that's f times a1, a2, right? But what's that? Scalar multiplication says that's fa1 times fa2, right? The component functions are that, right? What was our new gloriously unlimited definition of derivative? if you would like, if you're a math major and this is troubling you, you could say we're using a theorem. Theorem is that the derivative is component-wise, right? So this is ddt of fa1 ddt of fa2. So then what? Now we're looking at products of functions of time, right? So now we're back to calculus 1. We know the product rule, right? The product rule is true for each one of these. So lo and behold, df dt a1 plus f dA1 dt df dt a2 plus f dA2 dt. So I did the product rule once for first component, once for the second component. And then what do? You just undo the scalar multiplication, use the definition of vector addition, and rewrite this as simply df dt times a1 a2 plus f times dA1 dt dA2 dt, like so. And what's that? Well, you're looking at what? You're looking at df dt times a vector plus f times dA dt. Now, you said you could just pull f out, right? That's absolutely true as an identity if what? What does it take to just pull f out of the derivative?
F is not a function of t.
Right. Or like in terms of equations, we need what? We need df dt is equal to 0, right? If df dt is equal to 0, that means f is the constant function with respect to time. So pretty much all of the proofs of the properties I'm about to write down involve this kind of argument. All right? What else can you tell me? Well, what if I have my mind is blanking. Oh, here's the other two big ones is if I have ddt of the dot product of a and b, or if I have ddt of the cross product of a and b, there is product rules for these products as well. So this was the product rule for scalar multiplication by a function. There's also a product rule for the dot product. There's a product rule for the cross product. In particular, it is just what you'd kind of expect. It's dA dt dot b plus a dot dB dt. And this one is, now the order matters here, of course, right? Like you got to be careful. You can't just change the order of the cross product, so you got to do it in the order that comes to you. But these are also true. Now, if I was to prove these in the notation that I just used here, it would take us like the rest of class to prove the second one, right? Because you'd have like 6 terms, and then you'd have 6. We can do better. 6 product rules, yeah. 12 terms.
For the dot product one, if the dot product is just a number, why is it not 0?
Ah, A and B are functions of time. A and B are functions of time in this discussion. So, for example, and even if A dot B was equal to a number, this could still be interesting. So, for example, wait a minute, is this example 2? What did I do? Oh, I started renumbering my examples after I hit record. Okay, fine, whatever. Sorry about that, guys. Okay, so for instance, A of t could be equal to, oh, I don't know, cos t, sine t, t. There's one, right? Then, like, oh, that doesn't illustrate what I was just telling you. But let's do this one. And then we have b of t we could let be, oh, I don't know, minus sine t, cosine t, 1 over t there. Right? Just for the sake of discussion. We'll assume t is greater than 0. This should be interesting. What's a dot b in this case? So you take the dot product of these two vectors. So we talked about the dot product of I mean, this is a good question you're asking. We talked about the dot product of a vector before, right? Our vectors were fixed at that point. But now we're thinking about functions which take in a time and give you out a vector. So like, it's not one vector, it's a vector for each time. So there's, we've switched the goalposts here a little bit. And you might ask, well, what does that even mean? Like geometrically, what's going on? Well, the way to think about it is a vector valued function of time. There's a couple different things we could think about. The one thing we could think about is just what I talked about, like the space curve. As the time varies, you're tracing out the path with the vector, like r of t. It's just going to where the curve is going to, right? But what we're also going to think about is that along that path, we could attach a vector. We could look at what's called a vector field along the curve. And so you might not visualize these based at the origin. You might visualize these like based along a curve. And so as you look at a curve, as time progresses, you're attaching a different vector at each point to the curve. These would be the formulas for that kind of like vector field along a curve. So that's where we're going. But our vectors are now functions of time, which means we're thinking about not just one vector, but a vector for each time input. Anyway, a dot b here is what? Same thing as we did before, x times x plus y times y plus z times z. How's that go? You get minus cosine sine plus sine cosine. Those cancel, right? And then we get what? T times 1 over t, which is 1. So a dot b is 1. What happens when we differentiate these? So what should dA, so if we were to calculate dA dt, what's that give us? Minus sine t cosine t 1, right? What's dB dt in this case? Yeah, minus cosine minus sine. What's the derivative of 1 over t?
Negative t to the 1.
Yeah, minus 1 over t squared, right? So if we calculate the dA dt dot b, what do we get? If we calculate a dot dB dt, what do we get? Let's look at these separately and try to see how all this goes together. What's dA dt dot b? So I should be looking at the dot product of this animal here with this guy up here. What do I get? Looks like I got a sine, wait a minute. Yeah, sine squared, right? Sine squared t. And then what?
Cosine squared t.
Oh, plus cosine squared t? All right. It's a plus, right?
Yeah.
Okay, my eyes keep going to the other one because I'm a dummy. And then what? Plus 1 over t, right? How about the other one? We calculate a dot dB dt. What happens there? Looks like we've got minus cosine squared t, minus sine squared t, then what? T times minus 1 over t squared is what? Minus 1 over t. And so what does this all mean? What happens when you add these two things together? You get 0. What's the derivative of 1? 0. So even though a dot b is 1, which is kind of seems like boring, it's actually saying something kind of interesting. It's saying that this, ddt of a dot b which is equal to, dA dt dot b plus a dot dB dt is equal to 0. Now, the nuts and bolts of that is not trivial, even though the fact that the derivative of 1 is 0 is kind of trivial. All right. This actually is not that interesting. Let me show you one that's a little bit more interesting. So what if we have a unit vector? So if you have a unit vector function of time, in other words, for each time, the length of the vector is 1. It's not a constant vector, mind you, but at each time the vector has length 1. What equation would that tell you? So you'd have like a dot a equals to what? It's a squared, that's true. Fair enough. But what is it equal to then? That's equal to 1. By assumption, right? I'm a unit vector, function of time. Differentiate that. What does it tell you? Let's differentiate this using our newfound product rule for dot product, right? Differentiate this. What do we learn? We learn that dA dt dot a plus a dot dA dt is equal to ddt of 1. What's the derivative of 1? This is 0. Like, if you guys get this wrong, then I retract my comment about you making it through this course. I'm sorry. But the dot product is what? It's commutative, right? So this tells me what? This actually tells me that a dot dA dt is equal to 0. A unit vector, function of time, has the property that it is perpendicular to its derivative. Now, does that make sense? What would a dot something tell you? A dot something would tell you the part of that thing that's in the a direction, right? If this was non-zero, that would say that there's a component of the derivative of a in the direction of a, which is non-zero. That would say there's an increase in the a vector in the direction of a. But a unit vector cannot have an increase in its own direction, because that would mean that its length is getting larger than 1. That's why this happened. It has to be that the change in a unit vector must happen perpendicular to the direction in which it's going. It has to describe a bending of the direction of the unit vector. So an example of this would be something like this: a of t equal to, all right, you guys help me out, cosine t, sine t. We can do it two-dimensional. Let's do it two-dimensional. Cosine t, sine t, right? This is a time-varying unit vector, right? I can draw a picture of it, if you like. Unit circle, right? So here's a at a particular time t, right? What's the length of that vector? Come on. 1, right? So differentiate it. What's that look like? You get what? So the length is 1. We agree on that. dA dt is what? Minus sine t cosine t, right? So the direction of this curve